Okay, guys, if we're going to build anything further that starts to resemble a computer, we're going to have to learn to speak like a computer. And computers speak in binary, so we're going to have to learn how to speak binary. So let's say I saw this sequence of ones and zeros on the screen. Now, if I didn't know binary, and I'm just used to counting the way we normally count in a system that's called base 10, right? We're used to a system called base 10. I would probably say that this equals 1101, right? But in binary, this actually equals 13. Now, how do we get to 13? Well, to understand how we get to 13 in binary, let's first consider how we get to 1101 in base 10. The way that we do that, let me see if I can paste this here, is that we actually think about the places, right, that each of these digits here, the 1101, each of these digits are in a place. So we have a 1 in the ones place, a 0 in the tens place, a 1 in the 100s place, and a 1 in the 1000s place. And so what we ultimately do is we add these up, right? We say, oh, there's the 1 plus, there's nothing in the tens place, so there's nothing to do. We could actually add a 0 there for the tens place, plus a 1 in the 100s place, plus a 1000s in the thousands place, and that is what actually gives us the 1101. Another interesting thing is when we think about carrying in base 10. So if I had 1101, or sorry, 101, and like right, we like to add this when we count in base 10, and I decided to add to that 9, then what happens? Well, I know that I can only carry up to the value 9 in any given place. After that, I have to carry. So here, I know that 1 plus 9 is 10. So I put a 0 in the ones place, and I carry the 1, which we like to show by putting a 1 here, right? And so now the 1 carries to the tens place. Cool, right? Because now we don't need a 1 in the ones place. We need a 1 in the tens place. And then the 100 and the 1000 stay the same. So our number becomes 1110. And that totally makes sense. Now, let's look at how we get to 13 in base 2. So in base 2, the places are different than base 10. So let's write our number out again. All right, now our first place is the same as base 10. It's called the ones place. Our second place is the twos place. Our third place is called the fours place. And the fourth place is the eighth place. Okay, and then it goes on 16, 32, and so on and so on and so on. Now, if I add these up the same way, right, I have 1 in the ones place, plus nothing in the twos place, plus 1 in the fours place, plus 4, plus 1 in the eights place. Well, 1 plus 4 plus 8 is 13. Cool, right? That's how we get to 13. Now that we've done like a really unlucky number, how would we write a really lucky number like 7? What does 7 look like in binary? I'll give you a second to think about it. Pause the video and tell me. Well, if I want to get to 7, and in looking up here, I can see that there's a 4 and 2, that'll make 6. And if I have 6, and I need to add one more to get 7, So if I had a binary number that just was 111, that would equal 7. Because 1 plus 2 plus 4 equals 7. Now, let's say that we want to add to our number 1101. We want to add 1 to that number in binary. What happens? Well, 1 plus 1 in binary is 0, right? Because basically it forces a carry. So 1 plus 1 is 0, carry the 1. So we're going to carry the 1. And then we'll keep these other numbers. So let's go like this. So our number becomes 1110. Okay? So we know that this number is 13. And we know that this number is 1. So we should expect that our answer is 14. Right? So this should be 14. Let's see if that turns out to be true. Well, we have nothing in the ones place, so 0. We have a 1 in the twos place, plus 1 in the fours place, plus 1 in the eights place. Well, 8 plus 4 is 12, plus 2 is 14. So, indeed, that does add up. So we're starting to see how we can add in binary. Let's do the same operation up here, right? So we got to 110. Let's try to do the same thing. So let's do 1101. And now we need to represent 9. Well, if we want to represent 9, then we just think about, well, we're going to need a 1 because we know it's an odd number. And we're not going to need a 2. We're not going to need a 4, but we are going to need an 8. So what we'll do is we'll say 1, 0, 0 for the 4 in the 2 place, and then a 1. So in binary, 13 plus 9, right? Looks like that. Let's put the plus here. And just to make it clear, how did we get to 9? Well, 1 plus 8 is 9. Okay, now let's do the math here. So we have a 1 and a 1, that equals 0. We have a carry the 1, so and there's all zeros in this column, so we're going to just bring the 1 down here. And then we have a 1 in this column plus a 0, so we're going to keep that a 1. Then we have a 1 and a 1, that's a 0. And then we're going to carry the 1. So now we have a new sequence of binary. Now we need to evaluate the value. Well, there's a 0 in the 1's place, so that is equal to 0 plus 2 plus 4. There's a 0 in the 8's place, and then there's a 16, a 1 in the 16th place. So 16 plus 4 is 20, plus 2 is 22. And look at that. It's exactly what we would expect, right? If we were doing this in base 10, we would say, oh, well, 3 plus 9 is 12, carry the 1, is 22. So we've just done, now we just did the base 10 operation and the base 2 operation. So you guys are starting to see how the math works, the addition works in base 2. Now, what can we do with binary numbers? And we've seen how we can add them, and so it's obvious that we can use a binary number to represent a value, right? We can use this sequence of ones and zeros to represent a value in just a number on the number line. We can also use it to represent an address. So just think of it this way. What if we had, let's say, let me just draw out here. 3, 4, 5. I'm going to draw a top on this. Okay. And I'm going to copy this line. So I'm just drawing here, so pardon me, I'm just text drawing. And I'm going to copy these as well. Okay, and then I'm going to go down here, paste some more lines. Okay, so all I wanted to do was draw a grid of boxes that's basically 3 boxes by 5 boxes for a total of 15 boxes, right? So now I can use a binary number or a decimal number like 22 as an address. What do I mean by an address? Well, think about it this way. What if I labeled each of these boxes with a unique number? 0, 1, 2, 3, 4, 5, and so on, and so on, and so on, right? Then, if I wanted to reference a box, I could just give you the number. I could say, go to box number 3 and tell me what's in it. So you can think of that as an address. Now 3 becomes an address for that box. This is basically the concept of memory. We have this big array of spaces, right, of boxes, and we tell the computer to go get the value in that box at the memory address. You might have heard somebody say, oh, there's this value at this memory address. Well, that's what we mean. It's just a number that identifies the location in memory, the address. So in a particular box has a address, a name, and it has a value in it. So the value in here might be 10, okay, for example, or 11, or 55, or 42. It doesn't matter. It just has a value in it, and any one of these boxes can have a value in it. So you can use binary to represent the value 10 and the address 3, right? So we could say that at address 3, which we would write as binary 1, 1, there's a value which is 10, which we would write as 0 in the 1's place, 1 in the 2's place, nothing in the 4's place, and 1 in the 8's place. 1, 0, 1, 0, or 0, 1, 0, 1, right? Nothing in the 1's place. I got a 2 plus 8 is 10. So here you can see that box 3 points to the value 10. Another cool thing that you can do is you can say, well, the value here is actually just another address, like 5. So this could actually, so if this was the value 5, but you knew that the value wasn't a number, but it was an address, then you could go look in 5 and see that its number is 15. All right, that's getting a little complex, and we call that a pointer, okay? A pointer to memory. So this guy here, box 3, holds a pointer to 5, which is this box, and that box actually ultimately has the value 15. That's called a pointer. Now, sometimes when you have a number, and let's just make up a random binary number like 10110110, okay? Sometimes you have a number like this, a big string of binary numbers, but you actually only need to represent small values. And so instead of using the whole string of binary numbers to represent a value, sometimes clever people, just to save space, will say, well, the first three bytes, first three bits, right? Each of these digits is a bit. The first three, that's one value. The next three is another value, and then the last two here, that's a value, right? So that's called a bit field, and it's not important that you know that, but right now. But it's interesting to know that sometimes people cleverly pack multiple values into a single binary number to save space and be more efficient. Okay, so it's an easy way to kind of like embed lots of information into a single binary number. And ultimately, remember that each of these ones and zeros, they're going to represent some on or off state in a transistor somewhere. Well, maybe a little bit more complicated than that, but for now, think of it that way. Okay, so now you kind of have an idea about how binary numbers work and how computers speak binary and add binary. Now what we want to do is take this information and we want to use logic gates to, for example, add binary numbers together, right? So we're going to create a way to represent a binary number and feed it into a series of gates that can then do math and give us out an output that is correct based on base 2 arithmetic, specifically addition.